Energy diagram notes. Collision molecule activation energy. Reactant molecules must collide with proper orientation to each other when they collide in order for a reaction to take place. For instance, this iodine and bromine would not have a very effective collision. Instead, this molecule will rotate, or the iodine will rotate around to collide with a hydrogen molecule and then try to replace it to form a new bond. 2. Not all collisions produce a chemical reaction, some are ineffective. As we mentioned before, the rate of a reaction is equal to the frequency of collision times the fraction of effective collisions. So effective collision will put energy into key bonds to break them. So effective collisions help us break reactants so that we can form products. Break the bonds of reactants so we can form products. So reactant molecules must collide with enough kinetic energy to break their strong chemical bonds. Molecules with small kinetic energy bounce off without reacting. Activation, or E sub A. Activation energy, also known as E sub A, the minimum energy required minimum energy that must be supplied by collisions for a reaction to occur. So the larger the activation energy, the smaller fraction of molecules having enough energy to react on a collision, therefore the slower the rate of reaction. So key here is the larger the E sub A, the activation energy, the slower the rate of reaction. So if we want the reaction to speed up, we have to have the smallest possible activation energy that we can have. So in summary, there are for a reaction to occur, 3 factors must contribute: orientation, frequency, and enough energy. So now we're going to look at activation energy diagrams. Okay, we're going to sketch these. We're not going to draw them to scale. We're just going to sketch them out. So here we have 2 different kinds of energy diagrams, and we're going to look at all of these pieces. All of these pieces must be labeled in every activation energy or energy diagram that I ask you to draw or sketch. So first thing we do, we think of this as the course of the reaction, and this is increasing energy. So first thing we're going to do is we're going to label the reactant and product bars, or the reactant portion and product portion of the reaction. We have the reactants here. Let me change that size of that. Products here. Okay, and then from the reactants to the top of the peak, this will be E sub A, activation energy. From the product bar to the top of the peak is E sub A prime. And then if you would draw a dotted line over, the part between the reactant and the product is your delta H, just like we've known delta H enthalpy. Okay, so same thing here, we have reactants and products, because reactants turn into products as we progress along the course of the reaction. From here to the top of the peak is E sub A. From product to the top of the peak is E sub A prime. And then if I did that dotted line over, the space between the products and the reactants is delta H. So these parts need to be labeled. So 1, 2, 3, 4, 5 parts need to be labeled. And we'll talk about how we know the difference between these diagrams in just a moment. So reactants are the start of the reaction, products are the end of the reaction. E sub A is activation energy, also called the activated complex or transition. And E sub A prime, this is a prime value, it's considered prime. Products to the transition, and delta H is E sub A minus E sub A prime. You might want to jot this down in your notes. You will need that memorized for your notes. So endothermic and exothermic reaction. An endothermic reaction, heat energy is taken in from the surroundings and turned into potential energy in the products. We know this already. We've talked about endo and exo. As a result, the enthalpy of the products is greater than the enthalpy of the reactant. So the purple here, the light color here, is the same thing, represent what I've underlined in red. You need to know that delta H is positive. You should already know this. It's endothermic. When delta H is negative, it's exothermic. And the change energy of the products is greater than the change energy of the reaction, it's endothermic. When the change energy of the products is less than the change energy of the reactants, it's exothermic. So product first, right? Thinking of it this way, we always look at it and compare the change energy of the products in both cases versus the change energy of the reactants in both cases. When it's a greater than sign, it's endothermic, positive delta H. When it is a less than sign, it's exothermic and negative delta H. So for all 4 of these, we're going to describe if it's endo or exo and then justify. And so let me show you what we're going to do. So we're going to say the change in energy of the products versus the change in energy of the reactants for each of them. So change in energy of the products is how we're always going to look at these. Change in energy of the products versus the change in energy of the reactants. Change in energy of the products versus change in energy of the reactants. Now, I'm going to show you a shortcut to do endo and exo in a moment, but first I'm going to say this is the E sub A. This is the change in energy, not E sub A, I apologize. This is the change in energy of the reactants. So that's the, think of this as 0 to whatever you want to call it, 0, 10, 20, 30, 40, 50, whatever, but this amount versus this amount, right? This is your delta E of your products, because remember this is the product line, this is reactant line, and this is delta E of the reactants. So we definitely know in this example, we have greater energy, change in energy of the products. So here is E sub A, change in energy of the reaction. I keep saying E sub A, I apologize. Change in energy of the reactants. And this is change in energy of the products, so that is much less. We got this value and this value. This is delta E of reactants versus delta E of products. Okay, products are greater than. And then here we have change in energy of the reactants versus change in energy of the products. And that is less than. Okay, so we know from this previous set of notes back here, if we have a greater than sign, it's endo. Less than sign, it's exo. So this is endo, exo, endo. It just happens that I did it this way, no reason, rhyme or reason to it. Now, another way that I want to represent exothermic is I like to teach it this way. Think of this as your high-rise, right, to an apartment complex or a large building or a grand store of some kind, right? If your product bar is about to escape out of the lower level, then you're going to exit out the door, so that's exo. So if your product bar is lower than your reactant bar, it's exo. If your product bar is higher than your reactant bar, it's endo. You will need to be able to identify if it's endo or exo, but also be able to justify why it's endo or exo based on this system, meaning change energy of the products is less than or greater than change energy of the reaction, what makes it endo or exo. Okay, in your homework and on an assessment, and during assessments, you'll need to be able to do all these pieces. So we're going to label these 5 pieces. So this is your reactant. This is your products. Remember, from the reactant bar to the top of the peak is E sub A. From the product bar to the top of the peak is E sub A prime. And then anything in between, that's a horrible line, but you get the idea. Anything in between here, right, is delta H. So we've labeled the reactants, the products, E sub A, E sub prime, and delta H. Justify why it's exothermic. So that, remember, to do that, we're thinking always about the change in energy of the product versus the change in energy of the reactant. This is less than. We expect this to be negative because it's exothermic. To calculate delta H, we're going to say E sub A minus E sub A prime. Now, we're going to calculate it using our diagram here. We know delta H is equal to E sub A. Now, E sub A isn't from 0 to it, right? Because that's not E sub A. E sub A starts way up here. So be very careful to find from the reactant bar to the top of the peak for your E sub A. So 150, 200, that's 50. And then E sub A prime is from the product bar to the top of the peak. So 50, not 0, but 50, because this is where it starts. 50 to 200 is 150. So then I know it's negative 100. We're going to assume this is kilojoules. So we've been able to calculate and show that our delta H would be negative like expected. Okay, example 19b. Well, same thing. We're going to label those 5 parts. So reactants, products. From the reactant bar to the top of the peak is E sub A. From the product bar to the top of the peak is E sub A prime. Everywhere between, don't go past the reactant bar, just between the products and the reactants is delta H. So we've labeled the reactants, the products, E sub A, E sub prime, delta H. Justify why it's endothermic. Remember, that's when we're doing change energy of the products versus change energy of the reactants. This is much greater because this space, right, this is the space of E sub A prime right here. It's much bigger than the space right here. We accept a positive value. We know delta H is E sub A minus E sub A prime. Delta H is E sub A minus E sub A prime. So we're going to calculate E sub A. Remember, it doesn't start at 0. It starts at where the reactant bar is. So 100 to 400 is 300. And then E sub A prime is from the product bar to the top of peak, so that's 100. So that's 200. We'll assume it's kilojoules, as it probably is. Not even necessary for a unit, but you get the idea. It's positive like expected. Okay, for example 20, we're going to sketch, literally sketch. I don't even care how off scale it is. I just want to see that you kind of understand the basics of it. So first thing I would tell you is to focus on your delta H, because then we know where the product line needs to be compared to the reactant line. And again, I am not going to draw this at all to scale, nor do I expect that you will. So we're gonna do something like this. Why did I make this low? Because I know it's negative, right? So then we're going to label the parts. Reactant, product. From here to here is E sub A. And I didn't do a very good job. It should be more like right there. E sub A from here to here is E sub A prime. I do expect you to get it better than this. I was in a hurry there. And this value here is delta H. This time it asks us to figure out the value for E sub A. Okay. Well, we definitely want to say E sub A of the products changed to E sub A of the reactants. We're going to say this is less than. So it's XO. And then we can say delta H equals E sub A minus E sub A prime. What do we have? We have delta H is negative 30 kilojoules. We have E sub A, remember that's activation energy, 165 kilojoules minus E sub A prime. We're going to subtract 165 from both sides. So we get negative 195 equals negative E sub A prime. And then we solve for E sub A prime by dividing both sides by negative. So we get 195 kilojoules for our final answer, positive 195 kilojoules. That concludes example 20. So what did I include? I included the 5 parts, the proper sketch. I know it's exothermic because it's negative delta H. I used this to justify why I knew it was exothermic based on my diagram. And then I calculated for E sub A prime using the fact that we know delta H is equal to E sub A minus E sub A prime. Plugged in my values, did proper math, and got a value of 195 kilojoules of energy. Okay, example 21. First thing I recognize is this is going to be endothermic, so I want that product bar to be a lot higher. Again, you can draw more to scale if you wish. I'm not going to be that picky. I just want really rough sketches. It's fine by me. And then here to the top of the bar is E sub A prime. We know the space in between here is delta H. We know E sub A products versus E sub A reactants is much greater, so it's endo. And then delta H equals E sub A minus E sub A prime. We know delta H is 150 kilojoules. We know E sub A prime is 340 kilojoules minus E sub A prime. I'm sorry, E sub A, I think I might have said prime here. E sub A is 340 kilojoules. We're solving for E sub A prime. So I'm going to subtract negative 340 from both sides. I get negative 190 kilojoules equals negative E sub A prime. Divide both sides to solve for E sub A prime. Divide both sides by negative 1. And I get 190 kilojoules for my E sub A prime. All these parts must be included when asked to sketch. Thank you. Reach out if you have any questions. Have a great rest of your day.